Hello, everyone. You are watching the GeekNarrator podcast. I'm your host, Pavel Yapte. And today we are going to rock the JVM because I have Daniel with me, who is from Rock the JVM. And we are going to talk about functional programming on the JVM. We are going to compare different functional programming ideas, mainly coming from Java, Kotlin, and Scala. We're going to talk about what is functional programming and what is the future? What is the current limitation? What is the future? What are some myths around functional programming? Welcome, Daniel. And I'm really excited to have you and really excited to learn more from your experience on functional programming on the JVM. So welcome to the show.
Thanks. Happy to be here.
Awesome. So for our viewers, let's start with a bit of introduction about yourself, like what you do, and also a bit about your journey into the world of functional programming.
Right. So my name is Daniel Ciocărlan. I am a Romanian software engineer, and I founded this learning platform called Rock the JVM, which is a learning experience platform for everything in the Scala world, also on the JVM in a larger sense with Kotlin, some Java, some big data processing with Apache Spark or Apache Flink or things of that sort. So it's a little bit of a wider net, but mostly on Scala. It aims to cover the major tools in the Scala ecosystem. And my journey in functional programming started almost like 10 years ago, I would say. And I kind of fell in love with Scala as a nice combination of a very beautiful programming language and just very fun to write, which also mixed in, or rather has some embedded principles that were very natural to me. They were very mathematical. And these functional programming principles combined with a very fun and natural language for me to write led me to study Scala very much in depth. And I've been also writing Scala and teaching Scala for, I would say, 8 years at this point. And on my website at rockthejvm.com, I cover Scala in great detail with also the major tools in the Scala world, including Akka and Cats Effect and Zio and things of that sort. And filmed hundreds of hours of video, wrote tens of thousands of lines of code on camera, that sort of stuff.
Awesome. Yeah. To our viewers, whoever doesn't know about Rock the JVM, please go and check it out. It's really awesome. Like the way Daniel teaches about these complicated concepts, it's really interesting. And to share a fun fact, I also started my functional programming journey with Scala from Daniel's course on Rock the JVM. So it's pretty interesting. I recommend people check it out. So thanks for the intro, Daniel. Let's start with the very basic of functional programming, right? Like everyone knows a little bit on, here and there. There is probably a definition out there of functional programming. What is functional programming? And for a beginner, if I'm a beginner, what should I know to get started with functional programming?
Okay, there are very many levels that you can explain functional programming as. If you're coming to functional programming as a total newbie, I would start with a simple shift in mindset, because functional programming is a different way of thinking and approaching things. So the thing that I always start with when approaching Scala as a functional programming language to beginners who've never seen this sort of stuff before, I start with shifting the mindset from the code as set of instructions, which is what we're generally taught in school, and this is what we're generally used to when programming with, say, Python or Java or C++ or the more mainstream programming languages, in which you have to express your code in terms of do this, do that, for 100 times, do something else, like repeat loops. So you think code sequentially. Obviously, there's multi-threading to that and so on and so forth. But in general, every piece of code that you write is sequential. So do this, do that. We use instructions to do that. So the fundamental core element of a piece of code is an instruction. Now, in functional programming, we tend to think code in a little bit different way, which is in terms of expressions. So we say that a particular value has the form of, and you insert a big mathematical expression, which can be arbitrarily complex, and that thing evaluates to a value. It doesn't really matter to you as a functional programmer how that thing is being evaluated, but you think in terms of expressions, and your program is not a set of instructions that you need to manually enter and think about, but rather a program is a giant expression computing a giant value that can do an arbitrarily giant thing. So, for example, you can spin up a web server, Google search, or now the shiny new objects are these language models and AIs things. You spin up something like that by computing one big instruction that can potentially do a lot of things. And so instead of thinking your code in terms of do this, do that, and so on and so forth, you think code in terms of expressions instead. And in Scala, everything is an expression. Even, for example, if statements, they are expressions because they reduce to a value. They evaluate to something finite that you can then use later.
Yeah.
That's the first level that I would start explaining functional programming in terms of. So first of all, start to think code in terms of expressions. And then if you want to build bigger expressions, then you start using these functions. This is why the functional programming name came from. And the kind of complexity that you can arrive at by thinking of code in this way can be just arbitrary. So you can create arbitrarily large systems, distributed systems, big data processing tools like Apache Spark. You can build critical banking systems. You can build everything on top of these just core few principles.
Yeah, that makes sense. And I totally agree that, that mental shift is really important, because otherwise I've seen some badly written code in Scala as well, because the mindset was still from the, old world of imperative programming, where you're writing one instruction at a time and you're not thinking more in terms of expressing yourself into, at a functional level, like what you want to do. I think that makes sense. I would love to have a little bit more clarity on what do we mean by expression. If you could add a little bit more clarity on there. So let's say if I'm writing a Java based code, right? And I'm writing some instruction. Let's say I want to sort an array of numbers. So I write some expressions like for loops, and, I just iterate over it and I create a new array and return it. So is there also some expression involved, or what do we mean by expression when it compares with Java versus Scala, for example?
The punchline that I use for this is that in instructions, which is the fundamental building blocks of imperative programming, instructions are executed. They're being run in the CPU one at a time, whereas expressions are evaluated in the sense that they reduce to a value. So in that sense, when you start thinking in terms of whether it's executed or evaluated, you start to break down your code in terms of imperative versus functional, quote unquote. Because in a for loop, for example, in Java, you know that the for loop just executes things one at a time. So the for loop in Java is an instruction. It just goes through things one at a time. Obviously, it has some mechanisms for repeating and so on and so forth. But fundamentally, it's a set of instructions.
Yeah.
Whereas in Scala, a for comprehension is an expression because it evaluates to something. It can be a list or a map or things more abstract like options and futures and effects and whatever. So you can start breaking the code down into these two categories by thinking of whether they're executed in terms of instructions or evaluated as expressions. Obviously, Scala breaks down or compiles to Java bytecode, and this bytecode is evaluated on JVM, which is fundamentally evaluated on a CPU, which is instructional by nature. But we don't have to think about that as functional programmer.
I think this is a great, idea to think about it. What is evaluated and what is executed, and I pretty much like it. Just to take a little more example to add more clarity there. So let's say I have an array of numbers and I want to iterate over them. So when I say I want to iterate over them, that's again, I'm thinking instructional, right? Like I'm passing on instructions. But when I say that, okay, I have to sort this array or let's say I want to filter the even numbers from this array. That's an expression I'm making, right? And then there are sub steps. So what I can do is iterate an array, filter based on this value. Again, this is instructional. But when I say, expressions, so how do I think in terms of expression? Like, how do I get started with it?
Okay. So let's say you have a list of numbers and you want to just keep the ones that are, let's say, even. That's a very simple example. In a normal imperative code, you would say for elements in list, just put the even number in a new list and just return the new list or whatever, something like that. Or even not return the new list, but just store the even number in whatever list you allocated prior.
Yeah.
So this is an instructional way of thinking because you take each number one at a time and then you place that manually yourself into this buffer that you then use in your later code. In an expression-oriented thinking, you would say list.filter and you pass in a little function there, and the end result is a new list. So you know right by the structure of the code and also by the type signature of the code that you will evaluate that new structure, which is the expression itself, to a new list, which you can use later. So you don't really have to think about how those numbers are being filtered out and placed into the buffers and so on and so forth. You just see an expression, say list.filter x mod 2 is equal to 0 or something like that.
Yeah.
And that is evaluated as something else that you can then later use.
That makes sense. And yeah, when I think, because I don't have a huge experience in functional programming, I still think in a more imperative way, but I try to, force myself to think in more expressive manner where I don't go, okay, allocate this list because I am going to store the result of my computation in this list. That's already instructional because I know what is going to happen after my function is, executed. That's great. So yeah, I think this mental model is kind of clear to me, like how people should approach it and to get it right. Let's compare it a little bit with the object-oriented programming world, right? Like, are they like opposite of each other? Can they go together hand in hand? If we talk about functional programming and object-oriented programming, because typically like the way Java is evolved, right? Like it used to be like this object-oriented programming. We used to have these objects and, behaviors and state inside those objects. And then since Java 8, there was this streaming library where, you think a little bit more functional, but still somewhere between. So are they opposite? Can they coexist?
Yes, they can coexist. When I'm presented with a sort of comparison between object-oriented versus functional programming, I tell people that they're not versus one another. They're not opposites in any way. They're separate concepts. They're like apples and oranges. And programming is a different way of thinking and approaching code in general. Like I said, thinking in terms of expressions, passing functions as arguments. We can get to that later in the conversation. And object-oriented programming is a style of organizing your code in terms of these entities or these, we call them objects, in terms of classes, inheritance, and design patterns and everything that arose from those core few principles. And functional programming and object orientation can stay together and they can work very well, as is the case for Scala, for example.
Yeah, that makes sense. Given my object-oriented programming background, a little on functional programming as well, when I see at the real-world scenarios, like real-world applications, I try to focus more on the objects, the state and behavior. I think about inheritance, and I'm very much focused on defining objects. And then when I come to functional programming, this is when I'm actually writing the code. So is it that when you design your application, you think more from the object-oriented perspective, but when you're actually writing the code, you're more on functional, thinking? Is that the right way to think about it? Or
the way that I see this is you still need to organize your code in some fashion.
Yeah.
And in Scala, for example, you still have the same kind of object-oriented principles that you may be familiar with in other canonical object-oriented languages like C# or Java or whatever. So you have classes, you have inheritance, you have these sort of quote-unquote interfaces. In Scala, they're called traits.
Yeah.
You have enums and so on and so forth. And you have inheritance, polymorphism, generics. So we have these extra type systems that are being, say, derived out of the core object-oriented principles. For example, the core subtype polymorphism that you see in Java that's also present in Scala, for example.
Yeah. Mm-hmm.
So you have to organize your code in some fashion using classes, objects, that sort of stuff. The class hierarchy or the domain that you use to model your own application might or might not have anything to do with the actual implementation of those functionalities and with whether or not you approach your code or implement it with functional programming or not. So they're kind of separate concepts, and you can very, very well design your application with classes and inheritance and that sort of stuff using regular object-oriented principles and do functional programming. Or you can define your application as just plain functions that are playing around and passing between your application without too much object-oriented stuff going around. Now, it's a matter of choice, and it depends. Obviously, it depends on the kind of application that's being built.
Yeah, I think that makes sense. Let's go a little bit deeper into the understanding of functional programming. So I'm a beginner. I want to learn functional programming. What are some of the concepts that I should start with and, I should try to understand before even jumping on more complicated topics?
Right. One core aspect is this slight mental shift between imperative / instruction-oriented programming versus expression-oriented programming. This is one of the first things that I teach in my Scala beginners courses and in trainings at companies. This is the first start in a new direction in which you can point your code into. So this expression-oriented mindset to approaching code. Then another core principle is using functions as values. This is something that baffles a lot of people, especially in the beginning phases. How is it that you can pass functions as arguments? Is that a magical thing? And we can very much map this to a design pattern in object-oriented programming, which is, for example, the command pattern. This is very popular in object-oriented, like quote-unquote Gang of 4 design patterns. And we show people that this is very similar to object-oriented things. And this is how Scala actually implements some of the functional programming principles on top of the JVM, which was built for Java. So this was an imperative kind of machine. So Scala implements this sort of stuff using or leveraging some object-oriented principles. And the kind of parallels that you can make on that are that you can pass functions as arguments, but those functions are also instances of some classes that are being native to the JVM. So passing functions as arguments and returning functions as results are a new critical, let's say, crossroads in which you can shift your mindset a little bit. Another one is immutability, because due to the fact that expressions are evaluated to values, you then need to attach types to them, at least for strongly typed languages like Scala. And you have to think of these expressions as potentially new objects, because in functional programming, there is a potential pollution from what we call side effects. Side effects are these extra phenomena, let's say, that are happening outside computing pure values. So if we get back to your earlier very simple example, if you want to filter out some elements from a list, if you have a list of numbers and you want to keep just the even values out of them. So you say list.filter, whatever, you can pass in a function there. So you return a list. But what happens if you also print the numbers that did not make the cut? You print them to the console, you log them out. What kind of expression is that? Does it return a list? Well, it kind of does. But the theory of functional programming says that if you run the program multiple times, or if you evaluate that expression multiple times, it should always give the same value. But with the inclusion of side effects, these polluting elements in the code, we might not necessarily have the exact same behavior or same output if we run it multiple times.
Yeah.
So as much as possible, we would like to keep the code, quote unquote, pure by avoiding these sort of side effects that are behaviors that are outside computing normal values. For example, logging things, putting some data in files, sending things to the console, sending things through a socket. any sort of kind of useful behavior, even the conversation that we're having right now, is the application of a side effect. But we need to keep these side effects manageable, and they're managed in a variety of different principles. We can talk about those if you want. But in pure functional programming, we try to avoid those. And by avoiding those, we naturally come to think of, for example, data structures as immutable data structures, because mutating some existing data structures is a side effect due to the fact that if you run the program multiple times, they're not going to guarantee the same result. And that might lead to a whole suite of nightmares and headaches while running complex systems. These are some of the core principles that I would help or guide a beginner to shifting their mindset to functional programming in this style. And obviously some natural feeling of how you should orient your code will arise out of these principles, but these are some of the core things that I would follow.
Yeah, I think that makes sense. And these are really important and probably the toughest ones because, for a beginner who is, trying to take that first step and, make that paradigm shift, it's really important to understand this. Like first, the mindset shift. And the second one is to, passing in functions to other functions in more expressive thinking. Because I think that enables the expressive thinking, right? Because if I'm not able to pass a function to another function, I'm actually already calculating result. So it means that I'm kind of limited to my thinking when it comes to expressional thinking, right? So that is kind of required. And the third one is immutability. And that's a big topic. And, when we talk about concurrency, when multiple threads are, dealing with the same state and modifying state, immutability helps a lot actually, right? And a lot of frameworks actually implement that. Talking about the side effects part, right? So I know you mentioned that there are some strategies to, minimize the side effects that you want to have. And I think we can go a little bit deeper on that. But talking about the real world application, right? Like I think I'm always making some kind of side effects because I'm logging, I'm making a network call to another service. And I don't know if that is idempotent or not. I'm making some call to my database. I'm storing some state in memory. So there's always some kind of side effects that I have to make, right? Because, I'm writing an application and I want to, log more because it's a new application. I don't know how things behave and I want traceability into my application. So I need logging at all levels. So it's like injecting side effects at each level. So what are some strategies if you have to, minimize the side effects in functional world?
So the goal of pure functional programming is to have your code described by a giant pure function. That's essentially what a functional programming is, a giant pure function. And that function can be made out of other functions, which can in turn be made out of other functions and other values and so on and so forth.
Yeah.
So a pure functional program technically has no side effects, like in theory has no side effects. However, in order to build actually useful software, we absolutely must produce any sort of side effects. Even showing something on screen or putting some data into a microphone and sending it across the wire to your headphones right now, this is a side effect that has to happen in order for us to have a meaningful conversation. So the question is, how do we manage those? The way that, at least in Scala, we manage side effects still in a purely functional way is to describe some data structures, to invent some data structures that describe side effects. They're not producing the side effects themselves, but rather describing what an effect is going to produce when that data structure is being evaluated. That's called an effect. So we think of code as effects that we can compose purely functionally with the same principles, with for comprehensions, with functions as arguments, with everything that we've been discussing so far, and not evaluate them until the end of the application, called at the end of the world, when we hit start, and the whole data structure is going to be evaluated and therefore producing these side effects as the program carries forward. The difference between that sort of program, which is written in a purely functional way with data structures describing side effects, and an imperative program is that the side effects are not being produced at the time they're described, at the time the data structure is run, but only at the point where the data structure is being evaluated. And therefore, we can keep our mindset pure while composing this program and just evaluate all the side effects in the world after we click the run button.
Okay. Yeah. Yeah. That's a great mental shift, because I think it's all about mental shift, right? Because we write programs for our machines, but we also write programs for our fellow developers, for a team that is going to work on that in future. And the more simple code you write, the better it's best to, maintain your application, I think. And this mental model of, thinking in terms of functions and, reducing the side effects. And as you mentioned, side effects, we can think of in terms of effects, and that is only evaluated or, when the expression is actually called. And so is it some form of lazy evaluation of effects, or is it a different concept?
Something along those lines. So we essentially delay the production of side effects, not at the point where the code passes through for example, a logging instruction, like you would in an imperative language, but we simply remember, hey, I'm going to log this when the data structure is being evaluated. Mm-hmm. And then after the big giant function ends up evaluating all of those things, then a run loop will start producing the contents of every data structure in turn, and then it will start producing the logs that you were after, but only at the end of the world.
So there are still side effects because we can't get away with it, because anything usable you have to show to the user. Yeah, you create a website, you maintain some state, there is going to be some side effects, but it's not about not creating side effects, but it's about thinking in terms of minimizing the side effects while you're writing the code, right? That's the shift.
Yes, and encapsulating them in data structures that still behave purely functionally, that don't produce side effects the moment you create the data structure, like you would in a regular imperative language, but rather when you evaluate that thing where that data structure is being torn apart by the run loop, and then the program starts to actually produce the stuff. So it's the kind of analogy that I would think this, and I've never actually thought of it in this way. It's like a program is built out of these little fortune cookies. So imagine like a program being a giant, giant fortune cookie. When you tear that apart, you have smaller fortune cookies. And then you tear them apart and you have smaller fortune cookies. But at the tiniest fortune cookie, when you tear that apart, you get a little thing that's actually being read. So that is, for example, log something out to the console, or put this little buffer of microphone to my conversation.
Yeah, I think it's cool. Let's talk a little bit more on the immutability part, because, immutability is core of functional programming. You don't want to mutate data, but still there are some mutable data structures available in Scala, because, sometimes you have to do it. I don't know when. Maybe there are still ways to, use immutability, but why does then Scala provides you mutable data structures? Like, are there some limitations, some use cases that you've come across when immutability is not the right way to go about it?
Immutability works wonders in distributed systems, that I can tell you. So pretty much everywhere you have concurrency and or distributed systems, immutability works best, because tracing modifications in your code is bad enough in a single threaded piece of code. It's a nightmare in concurrency or in distributed systems. It's close to impossible. So immutability works nicely. The only concern with using immutability is potentially lots of allocations. However, there are a few ways that Scala and pretty much all functional programming libraries and tools will address those. One is the fact that Scala will leverage the JVM, and the JVM has evolved the garbage collector, and garbage collectors right now are quite smart. Even if you use immutability, Scala will keep references to the used objects so that you don't actually have to reallocate new stuff. For example, if you have a linked list and you add another element to the list, the old list is preserved. There's no point in allocating the entire list altogether. So that's a potential thing to manage. And the short-lived data structures that are being discarded are being caught by the garbage collector quite quickly. So I've rarely seen an instance where the garbage collector can struggle with so many allocated data structures. I only saw a situation once at a big company that I was doing an Akka HTTP training for, and they were dealing with some nasty garbage collection issues just because they were allocating data like crazy and they had extremely high throughput requirements. So normally that would not be a problem, but for a critical system like that, it might pose something along those lines. And what I would say is that if you get into trouble with garbage collectors in that sort of systems, you will probably get into garbage collection issues no matter what tool you use.
Yeah.
Because let's say somebody gave you a magic time travel pill to travel like 3 years back and re-implement this whole thing in another thing, like Java, for example, you would probably get similar issues. Now, this is not a proven theory, and this has not been statistically proven, but at least anecdotally, garbage collection issues with high throughput systems are sometimes a problem, regardless of whether it's Java or Scala or some other tool based on the JVM. Now, obviously, it depends on a case-by-case basis how those things are implemented, if you're leveraging the GC properly, if you're doing any tuning, and so on and so forth. So GC is a common sort of concern with immutability, but the GCs are quite smart. Another thing is recursion on immutability and the sort of stack frame allocation, because if you start to think in terms of functional programming, you quickly realize, for example, because we haven't talked about this at the beginning, you quickly realize that iteration is not an option. There's no such thing as iteration in functional programming. So you have to think of iteration as recursion instead. So for example, if you want to traverse a list of 10 elements in a more mainstream language, you would do for I equals 1, I less than 10, whatever, and then print out every number. But in functional programming, there's no such thing because the concept of iteration itself is instructional, and that's out of the window. So you need to think differently. And the analogous to iteration in functional programming is recursion. That's your go-to solution for any sort of repetition. So you start thinking in recursion. Okay, fine. But we know from recursion that every new function call put the little stack frame on the stack, and the stack is limited. And what happens if you try to iterate through, 100,000 elements or 1,000,000 or whatever? You go into stack overflows. So Scala addresses that, and many other programming languages address that through tail call optimization. That's called tail recursion. So that if you call a function recursively, if you organize your code in such a way that the last expression being evaluated is the recursive call to the same function with just different parameters, then Scala is smart enough to not allocate another stack frame, but rather replace the current stack frame with the new parameters and just replace that with a go-to in bytecode so that it don't have to allocate a new stack frame and then do the recursion over and over and over again, but just replace that with a go-to. So you end up eliminating all those stack frames that would otherwise cause a stack overflow. So this is another kind of concern that Scala has addressed with these tail call optimizations. There are a bunch more, but these are the first two that come to mind.
Yeah, absolutely. So just to summarize, looks like 99% of the use cases or applications in the real world are not going to face any issues when it comes to allocations because,
Not that I've seen, yeah.
Yeah. So, GCs are smarter and, as far as you're allocating the right kind of memory and not misusing it, I think you should be safe to use functional programming. And of course, you have to, look at it by case by case, right? You can't just say, okay, this is the general statement because some applications might have such kind of memory requirements. Let's say a high scale distributed analytics system might have some, memory constraints. So you might have to look at this, but generally it's not going to be an issue. So yeah, with tail recursion or, that optimization, that problem is also kind of gone. So, I mean, Scala is doing some kind of imperative programming at the low level to help you not do the imperative programming, right? Like, because
we naturally have to compile our code to something that normal CPUs can execute. So everything turns imperative at some point.
Yeah.
The question is how we choose to think the code that we write here at the keyboard.
Absolutely. Yeah. And that makes a world of a difference for complicated applications. So
yeah.
Let's talk a bit about concurrency. So, I would say concurrency and immutability go hand in hand when it comes to, functional programming, because you can't modify state. You have immutable data structures that you have to manage, and you allocate, new data structures whenever something is modified. What are some of the concurrency models you have seen? So for example, if I talk about Kotlin, there is coroutines, and then in Scala, there is, of course, these futures, but there's also actor framework that will give you a more sophisticated concurrency patterns. And then there is ZO actors as well. So what are some of the concurrency patterns you have seen when it comes to functional programming?
Okay, there are a few. One that it's being built into the Scala standard library is futures. And these futures are essentially a very simple abstraction for a value that will be computed at some point. And this primitive is based on asynchronous programming in the sense that you process these values by callbacks. You cannot really know when a future is done unless you either wait for it, which is a blocking operation and you don't want that, or by callbacks, which will be invoked by some other thread when the future completes, and therefore you can change the state of your application. But this quickly degenerates into what's being referred to as the callback hell, where anything sufficiently complex will resemble let's say, just a soup of callbacks that are being executed and triggering one another, and you don't have any clue of how to trace them. Another concurrency model, let's say, or another way to think about parallel and distributed code is this Akka suite of libraries. It's an entire toolkit that thinks code in a different way in terms of these little objects called actors. These actors were thought of as the original object-oriented paradigm. So back a few decades ago, the original ideal of object-oriented programming was to have these completely encapsulated pieces of data and behavior that you could not directly invoke like we normally do in Java now, but that you can only invoke asynchronously by sending messages to them. So you would send messages to an actor, and the actor would reply back or send messages further, just mimicking natural interactions between humans, for example. Because think of the conversation that we're having right now. It takes physical time for me to build my message in my head, produce it with my voice, and it takes physical time for it to go through the microphone, through the network, and so on and so forth, to get into your headset. And it would take physical time for you to receive it and process it, and maybe you would reply back. So this is the natural interaction. I can't poke into your brain and say, like, here's the information. So the natural interaction between entities in the real world were mimicked in this way by Akka actors. So the primitive for that is an actor with which you can only communicate by sending messages. You can never inspect an actor's internal state or call its internal methods in any way. You could only devise your application in terms of these independent entities that talk to each other in a non-blocking way. And you would, for example, if you have an application with multiple modules, you would have an actor that deals with showing this little preview on screen, an actor that listens for pieces of audio through the microphone, an actor that's being tasked with sending these buffers through the network, and so on and so forth. So actors with different sets of responsibilities, and they talk to each other to compose your big application. So that's one thing. And Akka built an entire suite of libraries based on these principles. We have Akka actors, Akka streams, Then there's a server API with, in the client API with Akka HTTP, there's Akka gRPC. There are all sorts of connectors to Kafka, to everything in between. There's also a distributed library for clustering if you have distributed systems, not just a parallel application on the same JVM, and so on and so forth. So this mental model gave rise to a whole suite of libraries and tools. So that's another mental model of concurrency in the Scala world. Another one is the Twitter style of writing applications. So from Finagle, and you think code in terms of functions, and these functions can be called asynchronous. And there is an abstraction called a future, but the future works in a different way than the Scala standard future because it also has interruption. It has a whole bunch of extra mechanisms for you to synchronize or desynchronize between the futures that are running at the same time. So there's a slightly different model in Twitter's mental model compared to the Scala standard API, although it is still quite similar. And then there's the effect systems like Cat's Effect and Zio. Cat's Effect and Zio work on the same principle, and that principle is separate from what we've discussed so far. And these think code in terms of effects. So these effects describe behaviors, for example, logging or producing plain values or interacting with a database or doing something on screen or processing transactions and so on and so forth. So these effects are data structures that describe what's going to happen when they're evaluated. This is something that we've discussed earlier, how to manage side effects while still thinking purely functionally. So Cat's Effect and Zio work in that way. And the way that those effects are being evaluated is through a thread pool that all the effects share. And these effects can also evaluate at the same time. And there's a concept that is very similar to Kotlin coroutines, and that's called a fiber in these effect systems. And you can manage these fibers with very low-level primitives such as, forking and joining them and interrupting them manually. So they're like low-level primitives that will allow you to manage pinpoint interruption, concurrent flow, and so on and so forth with the effects that you're managing. And there are obviously APIs to do that. So these are what I would say the major mental models in the Scala world for parallel, concurrent, and distributed systems.
Yeah, that makes sense. And, how do you compare like Kotlin's world of coroutines with, let's say, the fibers that we talked about? And I've heard that, with Project Loom, Java is also creating these virtual threads, which I guess previously were called fibers, but it is renamed now. So virtual threads in Java is still going to, differentiate between or decouple the kernel threads versus the virtual threads that they are going to have, but still they are going to have this callback hell problem because it still work on the same principle. Is it the same with Kotlin coroutines and Scala futures?
They're slightly different in different ways. So in fibers, you have pinpoint interruption and composability, which shares the same principles as any other kinds of effects, like the effects producing plain values and effects forking a new fiber and joining that fiber and managing a whole bunch of concurrent workflow have the same API. So Cat's Effect and Zio, the effect systems, will unify these APIs so that you can process these sort of effects in the same way, regardless of whether they're single-threaded with air quotes in between, or parallel/concurrent. They have the same sort of way of managing them. With Kotlin coroutines, the mechanism is a little bit different. And my student Ricardo and I wrote an article recently on the Rock the JVM blog about Kotlin coroutines, explained them in great detail. And we described there what kind of things that you can do with Kotlin coroutines, how you can launch them, how you can manage concurrency and forking them in a certain scope, and how their life cycle can overlap or not. So Kotlin also has a way of managing the life cycle of these lightweight threads, for the lack of a better word. And the style of managing them is a little bit different, but it is still a very similar concept in the sense that you have independent units of computation, which is what a thread is supposed to be, but having them very cheaply constructed, very cheaply interrupted, very cheaply canceled in large numbers, like in millions, on top of very few regular operating system threads on a single machine. So in that way, they're similar. Java Loom also does the same principle of creating new Java native threads very cheaply in large numbers on top of relatively few operating system threads. So that bit is very similar to the other two mental models, except that Java also wants to maintain their old APIs for managing threads. So, and they're doing that with a very clear intention to not break anybody's code.
Yeah.
Because in Java, the way that we manage threads would be to start execution, what are they called? Executor services, and manage thread pools and do interruptions, and which are pretty heavy-handed, and so on and so forth. So the kind of regular thread API, they want to maintain that, but do the million Java threads on top of 10 operating system threads behind the scenes.
Yeah. That makes sense. So yeah, I think talking about the concurrency part itself, the Scala ecosystem looks more mature, and there are more options to do concurrency in a better way, in a more functional way. If you have to compare, Kotlin and Scala in terms of feature set and, how easy it is to write code and how, pleasant it is to write code, what is your favorite, and what are some of the differences that you see in Kotlin and Scala?
All right, that's a big question. We can talk for 2 hours just about that. I love Scala. This is my favorite thing to do. So I'm doing effect systems, and I'm actually working on a project right now that will have a full stack application just written in this style. I also like Kotlin for the simplicity and the smoother learning curve. I would say that Scala has a steeper learning curve for a beginner compared to Kotlin. Kotlin also has some very low-level, high-control, difficult APIs to master if you really want to get really in-depth. But I would say Scala is it feels more unified in that way, especially if you're writing an effect system like Zio or Cat's effect. You stay in that environment and there's a sense of familiarity with everything else. Whereas in Kotlin coroutines, you have to kind of bring a new world into your existing application. Whereas in the effect systems in Scala, you pretty much stay in the same world and you just access different parts of it. This is like a completely 100% subjective feeling, so don't take that as gospel. But otherwise, Kotlin is very fun too. Yeah. So I've recently started to put out some Kotlin material on YouTube and on the blog, and people generally came with good feedback. So
I also like Kotlin, for its less learning for anyone who is coming from a Java background. But Scala feels more mature and more pleasant to write code, like complicated code. Like simple code, I think it's not a big of a difference. But when you get to write those beautiful for comprehensions and avoid those callback hell, so I think that makes a lot of difference, at least in my case. Cool. So I think we have covered a lot of ground. Let's talk a little bit about the current limitations when we talk about the Scala ecosystem, or current problems, or, things that you think, okay, this can be improved and, it will be improved in future. Yeah.
The Scala language itself is quite mature and quite powerful. Scala 3 is a great next generation version of the Scala language, and the adoption is growing. And I think that when people actually start the feeling of Scala 3, they will probably not want to go back to Scala 2 with the separation between the contextual abstractions, with a new macro system, with general pleasantness of writing code. Scala 3 is far superior. So I would give a giant credit to the Scala team to design this new generation language. Where Scala suffers in terms of developer experience, in my opinion, and as a Scala developer, is a bit of tooling, which is mostly based on a few build systems, the most popular one being SBT. And SBT might have a steep learning curve, especially if you're interested in just cranking out like my first Scala application. Like in JavaScript, you have create React app, just clone that, boom, and you have the first React application. In Scala, we don't have that yet. There are some attempts that have not really picked up too much steam. And this is what I also try to help with Rock the JVM with this little project that I'm working on, because I want to make this a template, a kind of general approach for building a full stack product on top of Scala. So we'll see how that goes. So with tooling and with the general pace of improving things, due to the fact that the Scala community itself is very small, very, very small. And the Scala community is disproportionately tamed or held by a few very passionate people, like a handful of passionate people that have produced these amazing libraries and amazing tools that everybody in the Scala world uses. This is something that we probably need to grow. The way to do that is still unclear. My role at Rock the JVM is to make Scala as approachable as possible so that more people start piling in, and so that we have some more pool of passion going into the Scala world. So this is my personal goal at Rock the JVM, to make Scala more approachable, more exciting, more easy to learn, so that more people start coming in and just start improving things. And this is the kind of major things that I believe would serve Scala well in terms of improvement. Obviously, there are things to improve, like in any programming language. It's like there are features that there aren't. I don't know. Maybe they're controversial, or not necessarily controversial. That was the wrong word. They're not 100% popular. Every language has that, or frameworks that become very old and very, very clunky, and as they grow and mature, they become these giant, I don't know, behemoths. Not really the example with Scala, because the libraries themselves are quite nimble and quite small, so that you can compose them easily. But things of that sort, they're inherent to any programming community, and with the Scala feature set and Scala tooling and Scala libraries are obviously no exception to that. So there are things to improve, and the community is. I really like the Scala community, that they're very passionate about wanting to make things better. So striving upwards, this is something that I particularly enjoy, and I want to be part of that at Rock the JVM, or with Rock the JVM.
Awesome. Great. I think we have, discussed a lot about Scala, about functional programming, and how one can, being a beginner, how can one get started with functional programming. So what is your final tip for anyone who wants to get started with Scala specifically, given they have some background with functional programming?
So the things that I'm doing here at Rock the JVM are kind of aimed at people that are interested in trying Scala out, regardless of whether they're experienced with functional programming or not. And trying something out, I would say, trying something that they would use, build something that they would use, get a real feel of what it's like to have something out. You can't get you can't get the true feeling of a programming language / framework / set of libraries unless you've built something tangible. So what I would say, and what I would advise people to do, is try building something real with Scala. I mean, try the general principles, try some toy exercises to get a feel of how these principles are matching your own set of expectations. And this is how I generally structure my learning materials, with deconstructed exercises. And after that, just start building something that you would use. I don't know, maybe you're interested in doing a file synchronizer with your NAS at home. Just write that in Scala, for example. Or build a little crawler, or build a whatever. Build something that you would use to get a sense of what it feels like.
Awesome. Yeah. Thanks a lot for the advice. Thanks a lot for sharing the experience. And thanks a lot for running Rock the JVM, because it is definitely making learning Scala easier and, growing the audience and growing the number of developers on Scala platform. So thanks a lot, Daniel. And, I really enjoyed, and I learned some of the mental models that will help me learn more on functional programming. So thanks for joining, and, thanks for sharing the experience. I hope you also liked it.
I'm more than happy to share pretty much everything that I know in the Scala world. So yeah, thank you for giving me the opportunity to do that.
Awesome. Thank you.